Hello everybody, my name is Bart Kippersluis. I'm the Communication Manager of Group 4 of the OGO Energy Challenge. The goal of the Energy Challenge is to drive a radio-controlled car around the track as efficient as possible. In this presentation we will start with an introduction, then we have 3 tests we want to discuss. First the dynamometer test, then the aerodynamic drag test, then the rolling resistance test. Then there is a programming aspect of this course, and then we end with planning of upcoming weeks and conclusion. To make sure the car uses as little energy as possible, it is necessary to study the energy conversion efficiency of the vehicle. This is called the tank-to-wheel analysis. The aim of the tank-to-wheel analysis is to determine the losses of all vehicle components in the vehicle at multiple speeds. The goal of the tank-to-wheel analysis is to determine the energy consumption of the vehicle per distance traveled. For instance, with gasoline cars, it's liters per 100 kilos. The tank-to-wheel analysis relies on various tests and calculations on the vehicle, which in this particular case is the model car. Having all these factors should result in a model containing the energy consumption of the model car. This information can then represent a basis for the optimal, most efficient driving strategy, which is also great important. As stated earlier, the tank-to-wheel analysis relies on the test and experience to determine specific losses in a vehicle. In this particular case, 3 tests will be performed. An air drag test to see at which configuration the car has the best aerodynamics, a rolling resistance test to determine the efficiency of the wheels on the road, and a dynamometer test to determine the most efficient speed for the car to drive at. As stated earlier, the results of these 3 experiments will be used in the tank-to-wheel analysis. For example, the total efficiency will be calculated with the results of the dynamometer, air drag, and rolling resistance. To make sure we actually drive the right speed at the test day, we need for the drive an indication of how fast it needs to drive. The car has 4 LED strips on the car, 1 at the front, 1 at the back, and 1 on each side of the car. We need to program these LED strips so the driver of the car exactly sees how fast he needs to drive. The second task we need to program is the toll payment system. The car will drive through a toll gate located somewhere on the track and then has to report himself using infrared beam. First, the dynamometer test. In the dynamometer test, the back wheels of the car are placed on a roller which is driven by a servo motor. The front wheels and the base plate of the car are fixed on the dynamometer. The dynamometer consists of 3 different tests. The purpose of the first test is to create a formula of the power to the wheels. We need this formula because we can't measure the power to the wheels, but only the power of the motor of the dynamometer. This test has already been done for us, so we can focus on the rest of the test. From the values of test 1, it is possible to create a graph. From this graph you can conclude an equation that you need to calculate the powers on the wheels. The main goal of the dynamometer test is to determine the most efficient speed for the car to drive at. We will do this in the second test. Because we don't know the forces that work in the opposite direction of the speed, called the load forces, yet we need to make a map of different speed and load forces, which we can read when all of the tests are executed. This is an example for a map like that. It's the efficiency map. On the x-axis you have the speed in revs per second, and on the y-axis you have the torque. And you can see at which speed and at which torque the car has the most efficient driving strategy. So you can see for this example it's around 25 revs per second. Not all of the power of the battery of the car is used to drive the wheels of the car. Some power is also consumed by auxiliaries like the LED strips. To determine the power consumed by the auxiliaries, we need to test the car in idle consumption. So that means when the car is at 0 speed. Now Oscar will tell you about air drag and the rolling resistance.
Hello, my name is Oscar Mannens and I will inform you about the progress we made on the aerodynamic drag test and the rolling resistance test. So first about the aerodynamic drag test. During this test, the model car will be placed inside a wind tunnel on a hanging platform, which is so that the car does not experience any rolling resistance. A force sensor then connects the front of the platform with the wind tunnel such that the aerodynamic drag force can be measured. The experiment will be conducted at a number of constant wind speeds, and we have been busy thinking of modifications we can make to improve the aerodynamics on the car. So one of the modifications, for example, is adding a rear spoiler to the car. We came up with around 9 different modifications, and we've chosen the 4 best, and those we are going to test individually in the wind tunnel in Cascade on the 3rd of December. So the goal of this test is to see which changes on the car improve the car's aerodynamics and thus reduce the aerodynamic drag on the car. Because if we reduce this drag force, the car's efficiency will increase, and reaching the highest efficiency is the main goal of this project. So as preparation for this project, we wrote a test plan which describes how the test will be conducted and which modifications will be made on the car. We included tables in the test plan so that we are going to fill in while doing the test. So if we do this for the 4 modifications, we then can see which changes improve the car's aerodynamics and which changes will have a negative effect on the aerodynamics. So of course only the positive changes will be made on the car. And then we would have our optimal car when it comes to air drag. Then the last test we've been working on is the rolling resistance test. The purpose of this test is to determine the car's rolling resistance at different conditions. This will be done in the form of a coast-down test. During a coast-down test, the vehicle will experience a negative acceleration, which eventually will result in a standstill. This is caused by the fact that the opposing forces act on the vehicle during the coast-down motion. One of these forces is the rolling resistance. Rolling resistance is the energy that is lost when the tire is rolling. The energy loss can be explained if we look at the image on the next slide. When a tire is rolling, the material in front has to be compressed while the material in the back relaxes, and this will result in an asymmetrical pressure distribution. This leads into a resistance and is known as the rolling resistance. During driving or coast-down motions, some energy will be lost in the tires. Therefore, it is important to minimize the amount of rolling resistance and to improve the overall car efficiency. In the last weeks, we have done research on properties of the tire and the relation of the rolling resistance. There are a few important factors which can contribute to a lower rolling resistance. One factor is the amount of camber. Camber is the angle of the tire, which you can see on this picture. Since the tire is deforming at the impact of the contact surface, since the road between the road and the tire, it is important to look at the concept of camber. By adjusting the amount of camber, the contact area can be designed to be relatively bigger or smaller. So we have to find out during the experiment what the right amount of camber would be for our car. Also, the performance during cornering can be improved due to a larger amount of grip at the outer wheel for a certain camber. During the rolling resistance experiment, we can determine if the adjustment of camber contributes to a lower rolling resistance by looking at the differences in acceleration. A lower deceleration means a lower sum of opposing forces and eventually a more energy efficient car. Furthermore, we want to determine the contribution of the electromotor friction on the total of opposing forces. That is why we have to execute this experiment with and without the electromotor friction taken into account. By executing this experiment, we can determine the rolling resistance force and the rolling resistance coefficient as well. We will execute the coast down motion several times. Also, we will adjust the amount of camber during the experiment and check the data by inserting the SD card into the laptop. In this way, we can also check if the values are realistic to be sure everything went good. These values will be used to calculate the optimal driving strategy in terms of efficiency. So after conducting all three tests, we will be able to determine the optimal driving strategy and optimal speed for our car to be able to reach the highest possible efficiency. If we know the optimal speed for the car, we then can program the LED bars on the car to show if the driver is driving at the right speed. Now Amin will give you an update on the progress on the coding part of this project.
I'm Amin. I will be talking about the programming and the planning part of this project. In the past few weeks, we have been working on getting the speedometer and the toll payment system working. The speedometer consists of two magnets on the cogwheel connected with a differential. Here you can see the two magnets. They're on the cogwheel and at the back is the differential. This means that for each rotation the sensor will output a high voltage. The sensor lies here, and every time a magnet passes, the sensor will output a high voltage. The sensor output is connected with the Schmitt trigger. The Schmitt trigger converts the output of the sensor in either a digital 0 or a digital 1 and sends this to the Arduino. This is to provide a clear signal to the Arduino. A LED bar on all sides of the model car will be used to display the speed of the driver so the driver can know how fast he is driving. With our code, we were able to measure the RPM and calculate the velocity of the car. We were able to do this using interrupt. An interrupt is a function that always checks for a condition and executes a piece of code specified by you if that condition is met. We used interrupt to measure the signal provided by the Schmitt trigger, and if that signal would change from a digital 0 to a digital 1, it would add 1/2 rotation to the amount of rotations. We decided to first measure 10 rotations and then calculate the RPM, because with the 10 rotations we can calculate the RPM and see how much time it took to get those 10 rotations and convert that to rotations per minute. We decided to use 10 rotations because when testing the code gave a consistent RPM reading. Because we now have the RPM of the cogwheel and we want the RPM of the tires, we use the gear ratio to convert from the RPM of the cogwheels to the RPM of the tires. Here you can see the gears. Here there's a small gear and a big gear, and this is the one that's measured by the magnets, and we have to get the RPM of the tires, and that is slower than the one measured by the magnets, so we use the gear ratio to do that conversion. With that and the radius of the tires, we can calculate the velocity of the model car. This velocity will be displayed depending on the driver's preference on the LED bar. We haven't implemented the LED bars as of yet. The toll payment system consists of a track side and a car side. The track side has an infrared transmitter and a radio signal receiver, and the car side has an infrared receiver and a radio signal transmitter. In this project, we use this toll system as a lap counter. Every time the car crosses the finish line, the car receives an infrared signal. The car should decode the signal and then send the radio signal back. If this all works correctly, a receiver besides the track is able to recognize which car just passed the finish line. The supervisors beside the track are then able to calculate the time the car took to complete the lap around the circuit. The infrared receiver had to be soldered and connected to the car. This was done using the circuit diagram provided by the instructors of the course. Because we consider planning important, we have a team role called the planner. The planner creates a deadline for each member using the deadlines provided by the instructors. This is not just deadlines for handing in the work on Canvas, but also deadlines for sharing your work with the rest of the group to get feedback and have sufficient time to make changes and hand deliverables on time. The planner also makes a logbook so we can keep track of what we did and how long it took. Using the planner, we will always be able to hand in deliverables on time. And we have made sufficient progress using that. Because of our progress on programming, thanks to wheel analysis and the test plans, we are very certain that we will be able to finish the project successfully and within the time frame. Thank you for watching.